Dear students, in the last class we have discussed about the electronic excitations. What is happening to the electron when it is excited from a ground state energy level to the higher state energy. That means when it absorbs UV visible radiation, in excited state molecule will be excited to the higher energy levels, and the electronic excitation also is taking place because the UV visible region energy is sufficient for a molecule to undergo electronic excitation. I have mentioned to you that when an organic molecule absorbs energy in different frequencies or different wavelengths, it will be undergoing different. If it is an infrared region, if a molecule is absorbing energy from the infrared region or energy corresponding to the infrared region, it will be undergoing vibrations. If it is a microwave region, the molecule will be undergoing rotation. If it is absorbing energy from the UV visible region, then electronic excitation takes place in the molecule. And this electronic excitation only will give us a clear idea of the changes that are occurring in the molecule, which becomes the reason for the photochemical reaction to give a product. So these are, then in the electronic excitation we also have seen the different types of orientations that are taking place. Sometimes the electronic retention of the spin is taking place, and sometimes inversion of spin is taking place according to the Hund's rule of maximum multiplicity and according to the Pauli's exclusion principles. We have seen how the spin orientation is taking place, and also we have calculated the spin multiplicity, and depending on the spin multiplicity we have named the state as a singlet excited state, triplet excited state, singlet ground state. Okay, so these are. Then we also have seen the different energy levels when a product is formed from the singlet excited state. It is a stereospecific reactions. When a product is formed from the triplet excited state, then it will be a non-stereo specific reactions. So all these things we have seen. Then now we are going to discuss about the types of electronic transitions or types of electronic excitations that are taking place here. For example, if you go through, for an atomic orbitals, when two atomic orbitals combine together, they will give two molecular orbitals. One is of lower energy called bonding orbital, and another one is having higher energy called anti-bonding orbitals. Two atomic orbitals A and B combine together to give a molecular orbital AB, which is having two molecular orbitals. One is of lower energy bonding orbital and another one is of higher energy anti-bonding orbitals. So the energy gap E2 is greater than the E1. Okay. Now what happens is the relative energies of the orbital. When atoms combine together to form a molecular orbital, and their orbital in which the electrons are occupied, actually we have seen that electronic configuration we know how to write for a molecule. For a molecule, when we write an electronic configuration in our basic classes itself, we have studied that it is a sigma bond, sigma star, pi star, and etc. 2px, 2py, etc. So when we write this, when they combine together, they take actually a different type of an electronic configuration, and they are occupied according to the increasing order of the energy levels in the orbitals such as sigma, sigma star, pi star, and non-bonding orbitals. So when we say sigma means it is an axial overlapping, very strong bond, pi double bond. Most of the molecules where the double bond is taking place, one is a sigma bond, another one is a pi overlap, it is lateral overlapping, and there are some non-bonding electrons which are not participating in the reaction or not participating in the bonding, not participate. For example, oxygen has a lone pair of electrons, nitrogen has a lone pair of electrons, etc. Now we should know what are the relative energies of the sigma pi and sigma star, pi star, and n. Okay, so these are the relative energies. Energy is in the increasing order. Then you have here sigma, pi, n, pi star and sigma star. So what happens here? Sigma and pi are a bonding orbitals. That means electrons can occupy easily. And n is a non-bonding. Sigma star and pi star are anti-bonding orbitals. Now what happens? We will see different type of excitations that can take place in a molecule. Different type of an excitations. Suppose if you take, for example, a simple molecule such as ethane, that is CH3. Now what happens? CH3 has one bond. This is a sigma bond. Sigma bond formed between the carbon and the carbon. Carbon and carbon combine together to form a sigma bond. So when the carbon and carbon combine together to form a sigma bond, they are forming two orbitals. One is a sigma orbitals and another one is a sigma star orbital. So energy is in the increasing order. So the first orbital, lower energy orbital only is occupying the electrons. So the transition is here, the possible transition here is sigma to sigma star. Same way if you take another molecule, okay, suppose CH2 double bond CH2, ethene, okay, ethene. Suppose if you take, what happens here, there is one sigma bond and one pi bond. Now what happens? There are one sigma bond combined together to form sigma star, sigma star, and again you have pi orbital combining together to form pi star. So these are the number of possible transitions. What are the possible transitions here? Sigma to sigma star is one transition. Sigma to sigma star. Another transition can be sigma to pi star. Sigma to pi star. Another transition can be pi to pi star. So third transition is pi to pi star. And the fourth transition is pi to sigma star. So these are the four possible transitions. Now for example, now we have seen the molecular orbitals involving sigma to sigma star transitions and the molecular orbitals involving the sigma to sigma star, pi to pi star transitions. Now let us consider another example. That is, suppose if you take a carbonyl compound. For example, third one, you take an example of carbonyl compounds. Carbonyl compounds, for example, you have ketone, aldehyde, or different carbonyl compounds. What happens here? Here oxygen contains a lone pair of electrons. So here this is a sigma bond, this is a sigma bond, this is pi bond and non-bonding electrons. Now the energy level diagram for these. Increasing order of the energy. You take here, what happens here? You have sigma, pi, n, pi star and sigma star. Okay, so the possible transition, what are the different possible transitions here? Possible is, the first transition can be sigma to sigma star transition. And the second one is pi to sigma star transition, then can be pi to pi star transition, fourth one is sigma to pi star transitions, then you have n to pi star transition and n to sigma star transitions. That means the number of possible transitions for a carbonyl compound is, now here the electrons are there, sigma electrons are there, pi electrons are there, oxygen is having a non-bonding electrons also. So the electrons, after absorbing the UV region, energy from the UV region, H nu, they can jump either from the sigma to sigma star, pi to pi star, or n to pi star and n to sigma star. So then what happens if you observe the UV visible spectra of a carbonyl compound? What happens? UV visible spectra, all of us have studied in our degree classes. Here x-axis it is a lambda maximum, here the percentage of intensity or the percentage of absorption. So according to these transitions, UV visible spectra should give you a 6 peaks, each corresponding to 1 transitions. But in reality, we are not having UV visible spectroscopy with the 6 peaks. That means there are some transitions that are not taking place. There are only few transitions only that are taking place. So now we need to know what are the, practically we need to know which are the possible transitions. Out of all these things, 6 transitions, which are the possible transitions? And in spectroscopy, we all of us know that for in the UV visible spectroscopy and IR spectroscopy, we have studied spectroscopic selection rules are there. Selection rules. As I mentioned to you earlier that the photochemistry and UV visible spectroscopy are very close to each other. So the first selection rule is based on the amount of energy we needed for a transition, and second one is symmetry of the orbitals. Symmetry of the orbitals. Now we will be seeing what are the different. But in reality, what happens is, for a carbonyl compound is having only 2 peaks. Lambda maximum if you take, absorbance percentage. There are only 2 peaks. One is pi to pi star and another one is n to pi star peak. The peaks which are showing a maximum intensity are actually allowed, most probably allowed transitions. Most probably allowed transitions. Allowed transitions only will give you more intense absorption bands, and less intense absorption bands are result of the forbidden transitions. Now, there is a doubt. There are 6 transitions are possible. Again, you have only 2 transitions. In that, again, there are one is a more intense absorption band, that means allowed transition, and another one is a less intense absorption band with the forbidden transition. Now, we will be calculating why some transitions are not taking place based on the energy. Based on the energy. Suppose if you take example, based on the energy, let us take based on the energy. So, what is the relationship between the energy and the wavelength? Energy is inversely proportional to the wavelength. So, wavelength decreases, energy increases. Suppose absorption is taking place at a lower wavelength, means it is having a higher energy. Okay, so we take, for example, if you take a molecule with sigma and sigma star transitions. We know that the transition to take place for an electron from sigma orbital to sigma star orbital, you need a maximum energy. Here the peak absorbed is at 130 nanometer wavelength. 130 nanometer wavelength. What is the meaning of 130 nanometer? It is the lower wavelength, but it requires a high amount of energy. It requires a high amount of energy. And for a molecule absorbing UV visible region or molecule absorbing radiation in the wavelength of a UV visible region, this transition is not possible. So here, because of the requirement of the high energy, sigma to sigma star transition is forbidden transition or not allowed because of the high amount of energy. Now we will be seeing based on the symmetry. So here again we have only 5 more transitions. Okay, then we will be seeing again the next reason is based on the symmetry rule. Symmetry rule. Now all of us know that symmetry rule always speaks about the gerade and ungerade. Two important words. Gerade means symmetry, the orbitals having center of symmetry or inversion center orbital upon rotation or inverting should remain it should keep up its original symmetry. That's what is called inversion center. And ungerade means orbitals which are not having no center of symmetry. That means their orientation changes upon the rotation or they have no inversion center. No inversion center. Now we all of us know, according to the selection rules, the transition is gerade to gerade transition is forbidden. Ungerade to ungerade transition also is forbidden. They are forbidden transitions. Now we need to know what are the orbitals that are gerade, what are the orbitals which are ungerade. Sigma orbital is gerade. It has an inversion center. But sigma star orbital is ungerade. Again you have a pi orbitals which is gerade. And ungerade. Pi orbital is ungerade, no inversion. Pi star is gerade. Pi star is gerade. So the only allowed transitions are gerade to ungerade or ungerade to gerade. So these are the only possible transitions. So in that case, another transition we can take now, sigma to sigma star being cancelled because of the high amount of energy. Now we will see sigma to pi star transition. Sigma is gerade. Pi star also is gerade. We know that gerade to gerade transitions are impossible. So this option also is cancelled. Again, pi to pi star transitions. Pi to sigma star transitions. Pi to sigma star transition. Pi is ungerade and sigma star is ungerade. Again, this transition also is forbidden transitions. Forbidden transitions. So, out of 6 transitions, now what happens? Sigma to sigma star transition is not possible because it is high amount of energy. Sigma to pi star also is not possible because they are symmetry forbidden transitions, and pi to sigma star also is not possible. They are also symmetry forbidden transition. Again, all the transitions that is only possible is pi to pi star and sigma to pi to pi star and n to pi star transitions. Now we will see what happens is now there are two peaks, isn't it? There are two peaks. That is, one is pi to pi star transition and another one is n to pi star transitions. The energy required for these transitions is very less. For example, you take this. This is a pi, n and pi star. So the possible transition is pi to pi star and n to pi star, n to pi star. Okay, so energy gap between the pi to pi star is more than n to pi star. Energy gap between the pi to pi star is, so energy is actually inversely proportional to wavelength. So higher the energy, lower the wavelength, lower the energy, higher the wavelength. That means the absorption maximum will be energy higher to pi to pi star. That means lambda will be is pi to pi star is less than the n to pi star, n to pi star. Okay, so these are the important transitions that are here. Now we will be taking, I suppose you understood now. Okay, now we will be seeing what is the difference between the pi. Okay, now selection rule is allowed transitions are most probable transitions. Forbidden transitions are less probable transitions. This can be explained. Allowed transition means most probable transitions. Probably the transition can take place between these two orbitals. Then forbidden transitions means forbidden transitions are less probable transitions. Now I have said the peak of pi to pi star is very intense peak because it is a most probable transition or allowed transition. The peak of n to pi star transition is very less. The absorption maximum or intensity is very less because it is a forbidden transition or less probable transition. This can be explained by the orientation of the orbitals. Orientation of the orbitals. Now we will see what is this orientation of the orbitals. Okay, suppose if you take pi orbitals. Suppose if you take pi orbital and pi, they are actually parallel to each other. They are parallel to each other. So the transition from the pi to pi star is very easy because their orbital orientation is parallel to each other. They are parallel. So the transition is the more probable transition. and also known as the allowed transition with intensity with absorption maximum or with intense peak. Intense peak. Whereas the transition between the N2 pi star, they are perpendicular transitions. They are perpendicular to each other. So, perpendicular transition, perpendicular to each other, perpendicular to each other. So, less probable transitions. Less probable transition, that's why they are less intensity. So now we will see, actually all of us know, we have learned from our classes itself that suppose you have an absorption, percentage of absorption or absorbance or intensity is plotted here, and you have a lambda maximum and you have a peak. Okay, lambda maximum increases this way. Now, if you have a more intensity peak, if the peak is shifted towards the more lambda or towards the longer wavelength, then that shift is called bathochromic shift. And that shift is towards the lower wavelength, then that is called hypsochromic shift. Hypsochromic shift. Okay. If the intensity peak absorption maximum is very intense, with maximum intensity means that is called hyperchromic shift. If intensity maximum is very less, it is called hypochromic shift. Hypochromic shift. So position of the absorption maximum also is depending upon the lambda maximum, position of the absorption maximum. So then what happens to an organic molecule? Depending upon the solvent in which this organic molecule you are making it to react. So influence of the solvent, on the position of the absorption band. Suppose you take a carbonyl compound. So this we will be discussing in the next class. Okay. Thank you.